across the switches which will enable us for a power flow from DC side to AC side also. I mean AC side to DC side as well as from DC side to AC side also. Here, actually what happens, let us consider a rectifier. This is nothing but a rectifier wherein the power from the AC fed to the DC. But basically this is not a rectifier. It's not a diode rectifier, it might be reading area, a diode rectifier or a thyristorized controlled rectifier. This is a normal PWM inverter which is operated as a rectifier. When we talk about a diode rectifier or when we talk about a thyristorized controlled rectifier, what was the characteristics? If you talk about a diode rectifier, it is nothing but 3 Vm by pi. If it is a 3-phase rectifier, the total voltage, if it is N1, it is root 3. So what happens if that is 3 Vm by pi? So this is the output voltage of a rectifier. When alpha is equal to, if it is thyristorized control, it is alpha cos alpha. So what happens when alpha is equal to 0, you get a maximum voltage 3 Vm by pi. If your output voltage, you know the rectifier, I think I did not explain. Now, first suppose whatever the average voltage which we are calculating is nothing but the output voltage. But when you are connecting a rectifier and if a rectifier is given a load in the DC side and if you start operating, will this voltage sustain of the same voltage appears across the rectifier? You understand my point? That voltage is calculated theoretically just by analyzing the output voltage waveform. You know how we do it. Now, once in practical, when we connect a load to a rectifier, will the same voltage, average voltage sustain? It will not sustain. It is increased. The voltage automatically drops. Even with grid network also, when you put a load, it will drop. But actually we have the grid recovery concept. So automatically again the voltage comes back to the normal state. Similarly, when you connect a layered rectifier, and if a DC load is connected to a DC capacitor to make the voltage constant, when you are changing the load, the voltage drops. If there is no controller, the dropped voltage will remain to be same. If you again add the load, the voltage much more drops, and again it will be constant. And the 3 Vm by concept will be again in the picture if you are going for a rectifier. First point. Second thing, when you are going for a AC to DC rectifier, I think you know what is the input source current waveform. If you remember, if you just recall the input source current, the input source current will not be if this is typically the input current of a 3-phase rectifier, when alpha is equal to 60 degrees, the input source current is like this for a diode rectifier. When the firing angle is increased to control the voltage, the current nature is much more degraded and the THP input current is much more degraded. So, when you are going for conventional AC to DC converter, where you need the conversion from AC to DC side, in all such things, what happens? DC side voltage regulation and AC side input current regulation is a challenging task. So, basically, using this high power factor converter, using the control scheme, what happens? You could achieve the rectifier wherein you can both control the DC output voltage and also the source current. For example, so let us take this concept. So what happens basically, this is the grid voltage and these are filter inductors and this is your inverter and you have a capacitor and load. Now what happens, this inverter basically operated in terms of feedback diodes, the power is fed from AC side to DC side, but it is operated or controlled to your controller. So what happens, basically when this is an engine, you need to generate the reference voltages for all these 6 switches. you remember the PWM technique as I was showing you before, you have the carrier and you have the modulation signals. The modulation signals are nothing but the reference voltage signals which you need to achieve when your converter is operated. That means when the carrier is there and with the carrier when you are interfacing your reference signal means the shape of the output voltage which you require is sinusoidal. So what you do the modulation signal? You use the reference of the sinusoidal and you generate the PWM signals, and when you give the PWM signals to the switches, the output voltage will be having the same shape of your reference voltages. In this case also, using the control scheme, we generate the reference voltages which are essential to operate these switches such that your output voltage will be controlled. That is, even though you increase or decrease the load, the voltage remains constant. And on the other side, your input current should be sinusoidal. That means, what should be the shape of the current that is drawn into the converter? Sinusoidal, and at the same time, it should be in phase with your grid voltage. First thing, right now we are discussing about rectification only. So, if you could keenly observe, it is easy to understand the renewable energy controller concept. So, if you take this concept, initially what happens when you want to regulate the DC output voltage, what we do, reference minus actual, star represents the reference voltage, X represents the phase. In this case, there is, in the DC side, you have only one, there is no phase concept. So you consider this as VDC star as reference and actual. So reference minus actual, you get the error is always taken as negative. So error, so it is due to the PA controller, then it gives the reference current. That is essential to maintain the current so that the voltage will be error will be zero. That means if the maximum peak voltage of your source voltage is 230√2, you may suggest a voltage of 1000 volts DC constant. So what happens when you suggest 1000 volts DC as a reference? Now your voltage should be 1000 here. So what happens? With respect to this is actual, the voltage is sensed from the DC side and it is given as actual. This difference is directly from the digital controller and error is found. The error is processed to the PA controller, and the PA controller, it is taken, it delivers the reference voltage. That means this is the reference current that is essential to charge the capacitor to get the recovery voltage. So ultimately what happens, this is the IDC. Now whatever the current that is being required in the DC side, where from you get this current, the current is again taken from source side. So what should be the shape of the source? It should be having the same shape of the source voltage. So this reference IDC is multiplied with the unit turn rate of your source voltage. That means if your source is Vm sin omega t, your reference is sin omega t. So what happens, that is multiplied by unit turn rate. So when this I is 2 amperes, whatever the instantaneously, whatever the source current shape is, the same unit turn rate is multiplied so that you generate the reference source current of the A phase. Similarly, if you just divide, because this is only for taking the common one from here, for 3 lines with A phase, B phase, C phase, what happens from here, this IDC is common and the unit turn rate for A phase is multiplied, B phase is multiplied and C phase is multiplied, and you are able to generate the source reference currents IAC star. That means IA star, IB star, and IC star are generated. So again the reference currents are generated. So what is the actual you send to the current sensor and finally find the IR. And this is processed to the current controller to generate the reference voltages to your switches. Now, so once if you do the control scheme, design control scheme for high power factor converter. Now, this will address your problems in such a way, because if I go more deep into the power electronics for matching of phasor and all, it's not possible now. So just understand the concept of control, how it works. So the results of the HPFC is something like this. So your reference voltage is something 6.6 KV is my reference voltage. So if you observe the current and the voltage, it is sinusoidal. Just in the before slide, I have shown you what is the nature of the source current if your firing angle is varying. The shape and even the current amplitude and the shape is completely divergent. But in this case, the source current is sinusoidal, which is increased with your voltage. Suddenly, if you are increasing the load, the current is increasing, but against it is following the same source current. So this is first thing. And if you see your THD, the THD is 1.82%, which is very less. As per IPP standard, the THD should be less than 5%. So here we see that whenever you are designing the system, you design the system such that it falls less than 5%. So what happens? This is first thing. Something intelligent and something interesting in hyperfract converters is they can operate in regenerative mode of operation also. That means in the earlier case I was telling you the power is spread from source to load. For suppose if the load is active in nature and if your source is nothing but it can